My name is Michael Jordan and I work at Context, and this is my colleague James Forshaw, and we're here today to talk about a new tool that we've released this week called CANAPE. So what are we going to talk about? So it's a new tool, CANAPE, which we'll be going through and demoing throughout the hour. But this tool is a very generic tool, allowing you to do a whole variety of different types of security testing, pen testing, product evaluation type work. But we're going to use an example of Citrix ICA as a worked example of how this tool can be used to ultimately exploit protocols like Citrix. Because in CANAPE we've got the ability to man in the middle of the traffic, and we'll be man in the middling the Citrix ICA traffic. We're going to be fuzzing the traffic, and then we're going to be doing a full exploit to get remote code execution on a Citrix client. And that one particular one is patched, and then we're going to show you at the end a nice sort of 0 day, which we use CANAPE in order to find. So first of all, so what is CANAPE? This is a binary network application testing tool. So if I ask the question out to the crowd here today, how many times have people tested network traffic, TCP traffic, and had to use some sort of tool? Have a hands up. 1, 2, 3. Look at that. Whole room. Brilliant. So when you go to try and you see this traffic coming out, it might be from an iPad device, or it could be from a Windows machine, it could be a random black box. There's traffic going back and forth, you don't know what it is. And you want to get into it, break into it, find out what's going on. And that's what CANAPE is designed to do. There are existing tools out there which allow you to do a certain amount of testing. So within sort of the web app HTTP world, you've got things like CAT and other web proxies, which are already set up to understand the protocol, get in the middle, a whole range of tools, repeating, fuzzing, etc. However, they only work with HTTP. There's tools like Echo Mirage, which allow you to get into the SSL writing sockets under Windows. That allows you to start to get into SSL traffic. There's other Python libraries out there, and custom code, and Wireshark. So Wireshark, you can see the traffic going back and forth, and we'll sometimes have dissectors for the traffic, depending on what it is. But generally it falls down to writing custom code. So there is no tool out there to start from scratch and write the whole TCP listener, forwarder, UDP, multicast, and do the fuzzers, repeaters. There's a lot of work then has to go in to build it up from scratch. So the CANAPE is therefore a framework, a sort of an IDE, which allows you to get down to working on the protocol and doing the security testing, which you're supposed to be doing, rather than setting up all the infrastructure around. It has all the support around it. So this is why we went for a new tool. It also has a nice GUI, so we're not just looking at Python scripts and stuff. We've got a full GUI. There's a picture there of sort of graphing of how it all displays out, which makes it a lot quicker and easier to get into the protocols. And it's totally free. You can go to the website, canape.contextis.com, and download it now. Okay, so how does it man in the middle, first off? So it supports various different man in the middling techniques. One is if you use SOCKS proxying. If the client, whatever it might be, can use SOCKS, you can then go through CANAPE on SOCKS, and it will then have that traffic man in the middle in terms of the actual TCP layer or UDP. Also, it can be used as a standard port forwarder. So rather than going to the real server, you go to a box running CANAPE and have that port forwarded onto the real server, allowing you to do the man in the middle. And it supports TCP, UDP, HTTP, it broadcasts the whole range of sort of IP upwards actual traffic. But we're talking about the application layer traffic here, not looking at the TCP UDP itself. We're looking at what's going across that wire inside the streams. It also has full SSL man-in-the-middle support, which will generate you the certificate on the fly, has a root CA you can install, so you can have still that trusted chain within the client. And it does this within pipelines. That graph I showed you a second ago, it allows you to sort of do a bit of proxying here, then passing it on to something to do a bit more processing, over here to log it, and you'll see as we go through the tool how you can build this pipeline and actual logic within it without needing to write any code until the point where you really have to. When you have got some funky encryption or some compression, then a little bit of code is needed then to do that logic. But the rest of the supporting stuff comes with CANAPE. Okay. So this is talking about now Citrix and ICA as a demonstration of how CANAPE can be used on a complex binary protocol. First question, is anyone here from Citrix? Hi there, good to see you. I hope you enjoyed my talk. So what is Citrix? It's a protocol used by the Citrix Zen app and Zen desktop products. So it's a bit like RDP. You can remote into a box and it will provide you with a GUI version of an application or a desktop, and then the mouse clicks and movements go back and forth across the wire. The application is actually run on the remote box, but it's done locally. So desktops and applications. And it has the bespoke client, which is running on Windows, Linux, on a mobile device. There's a range of different clients, which is obviously independent to the application itself, that's been run on the box running Citrix. And how it works is it has a configuration file, which gets downloaded onto the client, and will then tell it where to connect up to. So that the process flow, for example, there are different ways of setting it up, but the simplest way is you go to a web interface, you log in, gives you a list of different applications which are being published. You select one of those applications, and it'll download this configuration file. The configuration file looks a bit like this. This is a shortened version. This is a very simple ini file, which then comes down to the browser, and the browser then has the Citrix client installed. It understands the .ica file, launches Citrix ICA, it goes in here, and it'll tell it the IP address and where to connect up to. So to use CANAPE to man the middle of this, we want to, rather than connecting directly to the real server, but to go via CANAPE. And luckily, Citrix has support for SOCs, so we can change the ini file to put SOC support, telling it to go to a local instance of CANAPE, which will then actually proxy it through, and we can start to see what is this magical ICA traffic. So, first of all, James wrote CANAPE, and he's going to be demoing the various bits of CANAPE against the Citrix protocol. So, first of all, James, can you man the middle of the ICA traffic?
I can certainly try. So, I've got on here, XP machine, I have a VM running Citrix, and I've also pre-configured a connection. So, this is not going by SOC, so it connects up. Ignore the license warning. The license server crashed on it, I'm not quite sure why. And there we go, there's your desktop. So if we load up CANAPE, so you're first presented simple start screen, and just to make it get started a lot quicker, there's a series of templates. People can see this. So these are some of the templates we got: basic proxies, or basic proxies with HTTP parsing support. So if there's a protocol which is actually using HTTP as a transport mechanism, you can just sort of go straight into there. But here we just want to choose a basic SOCKS proxy. And this is what comes up. So it's pretty much like any IDE you're likely to see. So Visual Studio, Eclipse, these sort of things. You have a Project Explorer, which basically contains your resources. So in here you will have your SOCKS proxies, your HTTP proxies, all your services. In this default, it also has one of these graphs. So if I open this graph up, this is about as simple as you can get. So you've got the server node, the sort of purple node, is the place where traffic coming from the client actually enters CANAPE. It goes round, gets logged by a special node which logs, so it will not log unless you actually explicitly put something in to do so. And that then goes out to the actual server itself, and then obviously on the reverse leg goes the same way. So we'll start this up. Again, there's various things on here, but we can just go start. And if we load up our special SOCKS ICA, so obviously it seems to have done basically exactly the same thing. But now if we go back to our proxy, we now have our packets, and we can. So these are some of our packets which we've captured, and we can. There's various different ways of viewing sort of traffic. There's like a log viewer, so you can go to each packet in turn. This is your binary traffic. There's also, in this case, see if it actually works, basically histogram. So you can sort of see it's fairly constant across all the sort of byte values, so there's a good chance this protocol is probably encrypted or compressed or something like that. So that's all you have to do to do the initial SOCKS.
Cheers, James. That's brilliant. Right. So now we're looking more into the ICA protocol. So now we can see what's going back and forth. And now we start to wonder what's actually going on inside it. It's a stream-based protocol. It's one TCP connection that goes out, and everything's sent across the actual single TCP stream. So looking through what James was pointing out there, the different actual binary stuff, we'll see there's sort of three main parts to it. First is a hello, where it sends an ICA with a 7F7F at the beginning. That's saying hello, hello, back and forth. Then it goes into a negotiation phase, where the client will tell the server what it's got, the server will tell the client, and then they'll have a negotiation of how they're going to set up the main part of the stream. Then within the main stream, then the encryption comes along, the compression comes along, the multiplexing, the virtual channels, and the actual full data goes back and forth inside this main stream. So there's three phases: the hello, negotiation, then the main stream with all the data in. And we can see that by analysing that traffic. So James, could we please part it out? So we have a hello, and then we have a negotiation until we get to the main stream, please.
So I can go back to what I've already captured. So in order to do this, the net graphs can act both as a definition of how the data flows through the network you're providing, but it also can be used to provide state information. So in this case, we're going to use the graph to actually represent just two states in those three states, because realistically the initial hello is kind of unimportant to what we want to do. So the graph itself has a number of built-in functional nodes, which can also be then extended by actually dynamic content. But for now, we can actually just get away with everything standard. And the first thing we add is a nice rhombus, a nice decision node. So this is just a basic if statement. So when a packet arrives, it can then redirect it to two different routes, so either true or false. And in this case, we're actually going to use it as a state. So each connection maintains some sort of state information, and that can be queried in these nodes to affect which direction packets go. So if we call it if end of negotiation, for example, that's just the label, has no actual bearing on the functionality. And in order to actually do the true or false direction, we actually have to apply what are called filters. So filters, every time a packet arrives at a node, it runs a list of filters, and if it matches, it will actually consume that packet and do something with that, which might mean it tries to direct it down true or direct it down false. If you apply these, for example, to a logging node, you can actually then selectively say which packets you want to capture or not. But in this case, we're using a state, and the state's referred to by the hash value, end of neg. We want to match it against true and equals. So just as simple, if we're in the end of the negotiation state, so it sets to true, we redirect it via the appropriate direction. So in order to actually provide it, we need to connect this up. So we can just draw something on, and we add another logger node just to define the differences. So we say call this negotiation out. We call this negotiation, main out. So just defining, because the names will basically get represented in the packet log, so we can distinguish between the two. And the final thing is we need to actually specify which of these directions is true or false. And we can just collect it and type in our true and false directions. In fact, I've got them the wrong way around. Right. So now, if we are in the end of negotiation phase, i.e. all the negotiations finished, it will fire it out via the main out logging, otherwise it go negotiation out. Unfortunately, there's still nothing which actually specifies the state, so we still need a way of actually turning that on. And again, we can utilize some built-in functionality, and there's basically a series of library nodes. So this contains things like parsers. It also contains control elements. So one of them, this set meta node, allows you to specify the global state, a value in the global state, and it will fire when a certain packet matches its filter list. So we choose that one. Yep. And if we go and find the appropriate packet, which I just happen to know is this one. So this is the packet going out from the client which says, I've finished negotiation. We can actually copy that, paste it in place, and you don't need to restart. I'll just clear the log. And if we go back to our connection, unsurprisingly it still works, but if we look at our packet log, it's not worked. That's live demos for you, unfortunately. Sorry. Yeah, the reason I've not done it is because I haven't actually set these values. So you actually need to specify what value you're going to set, because otherwise it doesn't work. Yep, okay. So now we see we've got negotiation out up until the point it sends that packet, that 400 packet, and then it goes to main. And so this now allows us to separate out the two runs of traffic. We go back to the slides.
That's great, James. I'm loving it. Okay. So now we can see we're starting to get more into the actual traffic itself. By analysing the main protocol part, this is the bit that we're particularly interested in at the moment, we start to see that there's a framing around it. So the first 2 bytes represent 4 bits for the flag and 12 bits for the length, and then a run of data. So we can see there's this framing protocol in place, and we can now start to try to chunk this up. With HTTP traffic, we know the content length allows us to say how long the data is, and how we know the format of HTTP headers. But in this case, we need to work out what's equivalent framing through. So it's not just what's reading from the wire, we want to chunk it up in the correct sort of frames. So James, can we parse it out with the lengths from within the main traffic?
Mm-hmm. So I'll open a pre-existing one. So obviously you can draw that state on both directions. There is also a state model editor you can actually implement, which will do this for you. But just to save a bit of time, we'll go straight to an already created one. Just close that down. And obviously kill the connection. Okay, so in order to do this, because the state is actually a fairly simple protocol, and we can actually, if we actually capture some protocol data, so close that. Under our packet log, we now got our main protocol, and so we can see from here these first 2 bytes represent the length of the data, and that's then 2 bytes. And the hex editor provides you with various inspectors to select lengths out or select certain integer values. We can try and find one which is a bit more obvious, so 3 bytes, surprisingly matches 3 bytes, and so on and so forth. So it's a fairly simple protocol. So because it's fairly simple, we can actually also use the built-in parser editor. So in order to actually manipulate these little binary protocols, we're going to create a little sequence. And this sequence basically is the series of primitive values or other sequences which represent the data. So if we add main protocol, and then we can add various different types. But obviously, we've just mentioned it's a series of bit fields. So the first one was 12 bits, and that was called, we call that, say, length. This represents the length of the following data. And we also need to set it to little endian, because unusually for a network protocol, actually most of the values are little endian format as opposed to big endian or network byte order. You can actually set that as the default as well. So as the sequence, everything would then become little endian. So we add our flags or priority, which is 4 bits. And then we want our data. So it supports the concept of promoting data blocks to arrays. So in this case, we've added a byte, which is the constituent unit of our array. And we can then convert that to various different array types. And one of them is reference by length, because we've already got the length field. it's potentially different for every packet, so we need to actually reference that from the structure we parsed. And obviously you'll see this quite a lot, the use of the property grid to actually provide you the ability to manipulate the functionality. And in this case we want to change the reference value and it provides you with the values in the sequence you could possibly derive from. We choose length, and that's pretty much all we have to do. We can then add this to our graph during our main protocol route, and we add it as a special dynamic node, and from our property grid we can specify the parser. Need to add first a sequence parser, main protocol parser. Let me select that. And now, again, without restarting, we just clear that. If we then run our connection again, obviously comes up, and we will have a slightly different looking packet. So instead of the binary packet, which is the default representation, you now have this structured tree. So the flags have been parsed out, and the data, so that's our data set. And each of these now represents a single packet which will get carried along in the network, and they also know how to reconstruct themselves. So they know how to basically put themselves back together again. So that's that.
Cool, James, great. Looking good now. So the next thing we start to do is we start to look into the actual frames themselves. So we've got this lump of data, and so we want to see what the details are, and we see that it's encrypted. It's using a basic encryption algorithm. There are different ones in Citrix that you can have, but by default it uses this basic encryption. So we want to try to get into the traffic itself, so we want to get CANAPE to remove the encryption that's in place. So how does the encryption actually work? So looking through the data here, the packet highlighted there is the one that initiates the encryption, and after that it again gets encrypted. Further analysis, if I take two runs of the same thing, we'll notice that this byte at the end is different, and the top one is 1C, and the second one is 0D. And that seems to be the only thing that's changing on each run through the client, and then afterwards it's encrypted. So okay, so what's this look like? What is this further? So the next thing we did then is starting to look at there's a Java implementation of Citrix, which is quite handy for reverse engineering, quick and dirty. We can just extract it out. And here we found a little bit of code in the Java client, which is doing the encryption. And a diagrammatic version looks like this. So that on the X's at the top is the encrypted data coming along. To decrypt this, what we do is we get that key, which is that 1 byte from that packet I just showed you, single byte. It then gets XOR'd the key with the encrypted byte, and gets XOR'd with the previous byte. And in the first case, that's the key ORed with 43. So it takes 3 bits of information, the key, the encrypted byte, and the previous byte, XORs them and gets them back out again. And the key's in the traffic. So we've got everything we need to do the decryption. And byte by byte, each one is something like that. So should be quite straightforward, James, for you, I'm sure. Can you please man in the middle the encrypted traffic, extracting out the key?
Of course. So we will open again, just to make sure that I've actually done my job. So in this case, I've actually changed the graph slightly, because basically that's a reasonably complex graph, basically, for flow. So as we're now going to actually augment the parsing of the main protocol, I've actually subsumed all the main protocol functionality into a separate graph, and you can just refer to that as that, basically. So I'm not going. One of the things you can actually add when you actually run out of something CANAPE can just do for you, and obviously encryption, bespoke encryption, is something which arguably is not something CANAPE can implement. You can actually add it as a arbitrary .NET language. So if you add a script to your project, so this is some of the scripts you can put in. So you can have C#, you can have I am Python, I am Ruby, Desperate, Visual Basic and JavaScript.NET, and even F#, but you need the extension for F# because you need the compiler installed, and that won't get installed with .NET 4. But to not bore people, I'm going to actually just bring in this from an external file, because it's a reasonably complicated piece of code. And this actually now shows the way in which the dynamic content can actually interact with the networking model. So in this case, this actually represents an entire one of those nodes in the graph. And so for every time a packet arrives, it gets called, a certain method gets called, and then you can use XPath expressions, including things like actually doing equals and comparison operators to get the right path of that packet out. And that will actually select out a part of the data frame to actually manipulate. And we know that once we've parsed our main protocol, the data itself is actually represented under a data value. So this is why we're using /data. And this then uses, we've got two, one for encryption, one for decryption, because they're not actually symmetric. And we also need to capture the encryption keys. So this is, the decryption node is also doing the capture of a decryption key. If the packet starts with a 4, that means it's the key, and we grab the key, and we then set that in the global state, which is what we were using before to manipulate, to specify what protocol state we're in, and you can actually then reference that from anything else. So we add it to our graph. So obviously after the main protocol parser, it's very important. So we add this one, so we call that decryptor, and specify script, and it would help if I saved it, wouldn't it? And we specify decryption node, and we'll just copy that just to save us a bit of time. Because there's not much changing. So that will now be our encryptor. And we can specify a different node. Now, that's not a particularly useful graph, so we actually need to stick something in the middle. And we'll just stick a packet logger, because it'll tell us what we've been doing. Decrypted out. That's basically all we needed to do with that. So we go and run up our proxy again, create a server. Again, unsurprisingly, pops up. That. But now in our packet log, our text log will actually, we've got a text log as well, which will say we've got the encryption key, and we should now have decrypted out, and we can look at it. Unfortunately, there is still a problem. While we can actually look at this decrypted data, it still doesn't look massively decrypted. So there's still more to do, unfortunately.
Oh, come on, James, come on, we can get into this, we can do it. Okay, so we're into the encryption now. We can start to see certain plain text elements coming through. But James pointed out, it's not entirely plain text. It's not quite lining up with what we're looking for. And the reason is compression. Within the encrypted traffic, it's compressed. And the compression, looking at the Java code this time, is quite a lot of Java code. And there's quite a lot of stuff there in terms of the compression. It's quite complicated. So we don't really want to sit there and write entire code into CANAPE for doing the compression. So instead, we'll just turn it off. There's a registry key within Windows which you can set, that's it there, which will disable the compression on the client. By doing that, then we send through the client with the on and with the off, and looking at that negotiation phase we talked about earlier. And within it, the only difference with on or off is those bytes there. There's 2 bytes there highlighted. So if those bytes are set to 10 and 12, then it will get compression. It will negotiate compression. If they're just set to 000, then they won't get compressed. And then all the traffic will then go through uncompressed. So, James, what we need to do is we want to downgrade the compression and remove it by replacing those 10 and 12 with a 00. Can CANAPE do that?
It can certainly try. Right, so again, we've already pre-done the graph so that we've got our encryption and decryption on both directions. But in fact, this packet is actually coming in the negotiation phase, so we actually need to now manipulate the top level graph again. And so we'll choose one of the, again, built-in functionality. The aim was to really try and reduce the amount of coding you actually have to do, down to the bare minimum you would need. So in this case, we've got various mutators, and we'll choose this binary mutator node. So basically all this does is it matches a binary string and then replaces it with another binary string. Fairly simple. So yep. So we can specify in our properties our match, so 001012 as our match. We then replace that with 3 zeros, and that should be it. So if any packet comes past and has that byte sequence in it, it will replace it and then let it continue on its way. So we start this up. Connects. And we can now look at the packet log. If we look at our outbound packets, data, we should hopefully see, for example, username and passwords going out. Looks probably decompressed now. The various other information, your license key, yada 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 yada, etc. So that looks a lot better. Oops. Best not run Visual Studio, isn't it? Right.
That's brilliant, James. Now we're certainly getting into it. Okay, so now we start to analyse more of the traffic, going back and forth. James pointed out things like the username and passwords, going past in plain text. Oops. The other thing we start to look at, as I mentioned before, is what you're getting is a graphic of the application, and then what you're pressing and moving around and interacting goes back to the server, run on the server, then the graphics coming back and forth. So for example, we looked at the key presses, and because the keyboard being pressed, there's actually going to press down and up, get sent down and up through to it, and the packet starts with a type at the beginning, then it has a scan code, so this is the key on the keyboard that's been pressed rather than the ASCII character, because it's the application that's going to interpret that. Then there's another byte, and Mr. Citrix, you want to tell me afterwards what that byte is, I'd be appreciated. And then a marker on the end. So we can see, straightforward, you press a key up, down, sent back and forth. We can see that going through CANAPE. Another one then, we looked at as another example of how the Citrix product's working. A type D packet is when you move the mouse around, you get all these type D packets coming through. And it's a straightforward packet with the X coordinate, Y coordinate of whereabouts the mouse is on the image, the window, the button state, and then again another unknown packet, and the end marker there. And then the key presses, if it's got 1, it's no buttons, 2, it's press and up and down. So we can see straightforward, going back and forth. Now we're inside the encrypted and compressed traffic, how the actual protocol happens. So this starts to get more interesting. So what we really want to do here is we want to find some 0 days, we want to hack into, we want remote code. So we want to fuzz it. So now we've done all this work to get into the core of the actual protocol, we can start to fuzz at that level. Rather than fuzzing the encryption, the compressed data, we want to fuzz that plain text data, and then wrap it back up and send it back through. So for what we're going to do here, we're just doing standard bit flipping type fuzzing, because that's all we actually need. So James, right, inside the encrypted traffic, inside the compressed, can you fuzz the data that goes back and forth, and let's try and find some crashes.
Right. So just to make sure this actually works, I've already pre-configured the fuzzer. But again, CANAPE does come with some built-in fuzzers, but if that doesn't do it for you, you can always write your own in any of the languages. So for example, under the fuzzer tab, we have sort of the usual suspects, the binary integers, numeric strings, text patterns, all that sort of stuff. Basic fuzzers. And so in order to do that, I've added a byte fuzzer, which has various properties. So for example, you can specify where in the packet you want to fuzz. The filters can be reused to specify which packet you actually want to filter on. And in this case, I have actually added a filter, which is the packet we're actually particularly interested in. Obviously, no guilty knowledge whatsoever. We're doing this obviously live and stuff. I've also added a duplicator because normally it would just connect out once and this packet would come back once and you may get one crash or it may not crash depending on what you fuzzed. So the duplicator packet is another library node which will just match a certain packet and just clone it a certain number of times. In this case, we're cloning it 50 times. So if we start this up, now we're going to go pop into our XP VM just because it's a bit easier to see it crashing. So we run our fuzzer. Okay, we got a crash. That's good. Suppose we run it again. This time we don't get a crash, but we kind of get a strange size screen, which isn't quite what we wanted. So close that down. And obviously you can use the sort of standard tools to run and debug the processes as they load up. So we're definitely doing something interesting to it. The question will be, what is it? So we'll just close those down. And we're also logging the packets, so it will log both pre-fuzz and post-fuzz, and we can just do a simple diff of those packets to see what's been changed. And so we chose 10 differences, giving us 10 differences. And it obviously, there we go. So that's fuzzing.
I'm liking it, James, but I want to make one point that this is the old version of the Citrix client we're fuzzing before Mr. Citrix gets on the phone to the lawyers. This is not the modern one, okay? Okay, so we found it, we've got a crash in this old client. First we have a look at it, and it's a read violation. Okay, well, is this exploitable or not is the question. So, like I said, this is an old bug which has been patched. It was originally told in 2008, found in 2008. It was fixed in August 2010, 2.5 years later. And affected various clients, Windows, Mac, Linux, Solaris, and so it was obviously across the board bug. So this is an old bug that we're using as an example to demonstrate CANAPE. So that's why we're using SP. So having a look a bit more into this bug, so what's happening, what's going wrong. First of all, this is the location in the debugger where it crashes. So ECX is some offset into memory which doesn't exist. We're added to that fixed location. We can then see that the value from ECX gets put into AX, and various calculations go on to the point at the bottom here when it calls EAX. So we're influencing a part of the code which ultimately is doing a call. So we can control where that call goes to. We can therefore get code running. So further RE on the code, we see that this ECX, the value that crashed, has come from somewhere on the stack. Further analysing this, that there has come from this location, which come from this location, which has been calculated from here, from up to here, and has been calculated. And we control that bit. Put another way, in case you didn't follow that, which I'm sure you did, it roughly maps out like this. We control A as an offset into a list. And the bug is that it's not doing a bounds check on that actual offset lookup. So we can put in a value of A, which goes off into memory and pulls out a random value X. That value X is then used to look up into another list, which goes off and pulls out another random value from memory of Y. Y is then used to look up a function call, and then that ultimately does a value for EAX for doing the call. So there's a series of maths, operations, and lookups where our original value that we control will wander through memory, pull up random values, and then call something at the end of it. And what we need to do is make sure that the value of A will ultimately not cause any crashes on these reads into memory, and find a value for EAX, so it'll call EAX to somewhere in the heap that we control. That's what we need to do. Okay? So James, now can you do this? I bet it can't. Can you brute force a value for that particular location until we get somewhere in heap memory with EAX?
So, let me just close this one down. Oops. Nope. So, obviously, part of the problem of actually brute forcing this particular packet is that we don't always get the same traffic back from the server. So, in order to mitigate this somewhat, CANAPE actually provides you with the ability to specify scripted servers and arbitrary servers. There's some built-in functionality which basically allows you to replay certain lists of packets depending on input and output events. And so in this case, we've sort of distilled our list of packets down to this number. So some of these are actually, these are all the packets which will get sent back to the client. And we combine this to a replay server. So we're running on port 1494, which is the Citrix port. We've specified our list of attack packets, and under replay entries is basically our configuration of which packets to send when. And again, it's using the filter idea, so when a packet comes in, it checks whether it matches a certain filter. If it does, send back a list of packets. So if I start this up, and we'll go back to XP. So the change I've made in this from the previous one is that we actually want to specify a small bit. So if we'll actually look at our attack packets on our exploit packet itself, we know through obviously laborious testing beforehand that these 2 bytes seem to be the actual bytes of importance. So we just want to fuzz those particular bytes. So everything's configured in there, and then we've got a binary integer fuzzer, which will basically just increment a counter for each connection and just change those bytes. So run this. So we go direct, because we don't need to use the proxy server anymore, because actually CANAPE is just implementing the server for us. We run that. We got a crash. Cool. Try and run it again. Nothing happens. So obviously we're off a bit. Nothing happens again. Oh, a different crash. So we're definitely affecting it in some way. And hopefully that one. So we've now got a crash, which is actually a reasonably low address. It seems to have jumped to a memory address. It's a reasonably low number. There's a good chance we can probably heap flood to get there. And we can stick in our shellcode, and then we've got code execution.
Great, that's what we're looking for. So we've got our value in heap now. So that complicated route going through by pure brute forcing, we're calling somewhere in the heap. So what we're going to do when we get there. So James mentioned we're going to start trying to heap spray, because we're calling into EAX, which is a random location in the heap itself. And what we need to do is get memory at that location, such that when it calls there, it will be our code that's in place. There's a few obstacles here. So we're going to heap spray down by filling up the memory, but it's going to look something like this. We're going to end up with blank bits of memory. We're going to end up with our not sled and our shell code, and also we're going to end up with a header in front of each of the heap blocks. So that's what the heap's going to look like when we actually get there. So how can we get it to run through to ultimately our shell code when we've got these other bits in place? So first thing for doing the heap spray, there was a nice little feature of Citrix, where it uses a static buffer for all the packets that are coming in. And so if you send in one large packet, it would fill up this buffer with the length, the type, and all the data. And then if you sent in a short packet, like this, which had a long length, it would be put into that buffer. Now it's using it for the shorter packet and the data, but the length wasn't really checked, and it would use the rest of that memory after that. So we could send one small packet with a long length in it, and it would just copy out of that static buffer and send it into the heap. So lots of small packets will actually fill up the heap with large blocks of memory because of that length. That's going to allow us to fill up to that location, because it's going to copy all that data. Okay, other problem we had is this uninitialized area of memory, the zeros. So if we end up calling into the zeros, it's going to have to execute the zeros. And in this case, the opcodes of 0, 0 equates to incrementing AL onto EAX, where EAX points to. Now, luckily for us, EAX is the value that we've called. It's a valid pointer in memory, so that's fine. That will run through, and it won't cause it to crash, so we've got no problems. So we can execute the block of zeros, which are just adding a value to a random location in memory and not crash, because it's a valid pointer. Next problem we've got is that the header on the front of each of the heap blocks, and this is under XP, has this structure. So it's going to run through all of these zeros, then hit this header, and we need it to get to execute this successfully. The difficulty is the fact that the cookie value here is a random value, in that it changes literally every time. So we need to have a way that we can safely execute this as opcodes. So, but the size at the beginning is what we control, because the size is a factor of 8 of the actual size of the block. The size of the block is the size of the packet we send. So we send a packet of a certain size, that size divided by 8 is put into that location there in memory, and that's going to be the first part it tries to execute. So we needed to find some sort of opcode which will allow us to safely execute this without crashing. And we found, luckily, 8100 ends up being equated to this. So it will go to EAX again and dereference that, which is fine, that's safe. It will then add on the following bytes from the header structure. And because those bytes are the previous size, the cookies and the flags, it will just add that onto the location of EAX. So that's fine, that doesn't matter what those values are, it will always work and execute successfully. So we ended up with something looking a bit like this. We're going to jump into somewhere in memory, which will have the block of zeros at the beginning, which will execute through safely. We'll then hit that header block there with the 81 at the beginning, which will then add on the actual value of the cookie onto AL. So that there is a random value we don't control, but it doesn't matter because it's just going to add it on. And then there's no ops afterwards, is the beginning of our packet that we've sent across, which we've got our not sled, then into our shellcode. There's a few other bits of jumps in there to get around certain packet structures and stuff, but ultimately that's what we've got in place. Okay, come on James, we can do this now. We're going for the full route. What I need you to do, end-to-end demo, right? First we need to do a HTTP ICA file down, because we need to get somebody to come to our malicious server. In order to do that, well, you can create a web page which will download an ICA file, which will then be automatically, without prompting the user, get them to connect up to whatever's in the file. So malicious web page downloads ICA file, and the ICA file will then instruct him to come to our instance of CANAPE, which has the exploit in it. So first we need a HTTP to send out an ICA file. Then we need to replay that negotiation, so the hello and the negotiation, which also to set us up to get into the mainstream of the traffic. Then we send one large packet to prime that static buffer I mentioned, which will fill it up, which will have our NOPs there, our shellcode and everything in. Just one of those, please. And then you send like 5,000 of these small packets with a long length, that allowing the heap to fill up to the location where we're actually going to call into. Then ultimately send in the trigger packet, the one that we found that magical value, which will end up calling EEX into the heap. Can you do that, James?
Right. So obviously we can extend the previous one we've done. So we already had the makings of a basic replay server for the Citrix. The only real difference between this one is now obviously we've primed our packet with a particular value, in this case B703, and we've also added a flood packet, and so this is the packet which we're going to send multiple times so that we can actually flood the heap. Now obviously notice there's only one flood packet, and that's because the configuration can allow you to specify a mechanism to duplicate that repeatedly, and that is what we're doing. We've also got our HTTP server. So CANAPE does actually have a built-in simple HTTP server, kind of for this exact reason, so that you can actually serve it content. It's not the fully featured passing different things. It'll either send you data, or it will send you a 404 not found. But obviously our particular data itself is just a basic ICA file, which points to our server, and that will get served. So if we start that up, running on port 80, we can start up our replay server on here, and crucially, make sure I've got a copy of Netcat running, otherwise we won't see a lot. So we just listen on port 4444. Obviously, I left the client running on the XP VM and it reconnected to my server and exploited it. But there we go. That we do have root. Yeah. So yeah. Oops. Yeah. Cool. I made my life easier. Right.
Brilliant, James. I love it. We've got root. That's great. Is that all that CANAPE can do? Is it only anything it's good for, or can you give us any other examples?
Probably.
Yeah.
Okay, so in this particular case with Citrix, we're in the traffic, so we can do potentially other stuff with that traffic. So one of the things we did, we showed before the packet which was used for keyboard presses. So it would be kind of nice. Just shut this down. To maybe replay some keyboard presses back to the client. We can get in at the low level, send them quite quickly, all that sort of stuff. So going back to our original graph, our original proxy, if we start this up and do a server connection, hopefully I won't need to reboot the Citrix server, and I do. Very sorry for this. I think because obviously I'm connecting and then forcing the connection down, for some reason it hasn't. It gets into a slightly confused state. Probably if I logged in as a different user it would work, but fortunately I've got a connection already done. So connect up. So we're back to our desktop. And if you give this a few minutes, obviously, for everything to wake up, we'll come back to it in a second. So we've got an active connection coming through, as you can see from there. But some of these other tabs are potentially interesting. So for example, the active graphs basically allows you to see some of the state of the graph. In this case, I've hidden most of the nodes on those graphs, but this basically represents the individual parts of that, and we can see number of bytes transferred, number of packets coming in, all that sort of stuff. We can also see under that one, you can also specify the meta, and as you can see, the metadata contains basically our state, so you can say end of negotiations true. Also our encryption keys in there, so we can see that. But what we're interested in is the injector. So the injector, so once you've created your graph, rather than having to then tear down your connection and actually add some code to copy some packets around and that sort of stuff, one of the advantages of the GUI CANAPE provides is the ability to take packets from over here, throw them into a different context, and replay that information. And that's what we're going to do here for the keyboard presses. So I've added just a little extension just to save me some time to generate packets which do Citrix scan codes or basic scan codes and send the Citrix packets along. So we can type in, I don't know, hello black hat. When we click OK, it's now generated us a series of these keyboard packets, including shift state and all that sort of stuff, which would be quite time consuming to do. So we go back to our client. So just say open notepad, just so we can see in action, hopefully. And there we go. So that's one of the things you can do, and obviously it's the GUI really which gives you that sort of flexibility, the ability to just add extra stuff in as it's going along while the actual project is running without having to tear it down, recode it, reconfigure it. And so.
Okay, all right, yeah, so you can do more stuff as well. Okay, I'm with you. But come on, that bug was like 2-3 years old. You know, when you've been writing this, 4 years old. You know, is there anything else it can do? Maybe or against a modern Citrix client or against a server? Come on, you can put one last thing out the bag for them. This is Black Hat.
And as I said, demo only. Hang on, so we have our server running. So while obviously we can create arbitrary services, which is good for attacking clients, and basically using the same sort of infrastructure you can create scriptable clients or pre-configured clients to actually attack servers. And in this case we've got some packets which we found using CANAPE which will cause an interesting effect to happen on a server.
Careful.
Depends on what you define as interesting. Obviously I'm not going to give you more information than that, but the attack packets is basically a list of packets, and then this attack client is what we're going to use to actually attack the server. So we bring the server up, and if we go start, see there's a red bar. This is actually VirtualBox because VirtualBox can't seem to display the blue screen. So yeah, that's certainly an unorth DOS against Citrix. So there we go.
There you go, that's CANAPE. It's a binary exploitation tool. It's not specific to Citrix, and we apologise to Citrix if we caused any offence during today's talk. That was not the intention. It was just using an example of a good complex protocol that compiles out. But CANAPE can do a hell of a lot more. That was just the example. Have we got any questions? We have a question at the front.
Time have you spent on developing this tool?
The question is, how long did we spend doing this tool? I think James did it Monday or Tuesday this week, was it?
It's knocked it out. It's a few hours. 12 months, something like that. On and off though, not continuous development, as and when things need doing.
And it's fully non-commercially available.
It's fully available for free, download now, exact same version you've seen there. Question? Sorry? Windows only?
Definitely the GUI side of things only really works on Windows. It's Windows Forms GUI. The rest of the code, I have gone out of my way to try and make it compatible with Mono because it is a .NET 4 application. But you would need there's a basic command line client which will hopefully get released sooner or later. But it's the thing is the GUI is the main thing. So until I or someone else is brave enough decides to write a GTK sharp GUI, it's probably could be considered Windows only.
Any more questions?
Yes.
Yep.
How many parser do you have?
So how many
Parser?
Parsers.
parsers? How many parsers do we have for CANAPE?
Of the built-in ones, there's only a couple of basic ones, mainly for infrastructural reasons. So HTTP, for example, is a built-in parser. DNS is a built-in parser, just because they kind of fell out of the infrastructural code. As we go along, that template thing I showed right at the start can introduce pre-configured parsers. You can also add more script templates, so there's the potential to actually specify the script to do a particular protocol and actually add it as a template for future use. But at the moment, it's the case of just we've got to write them, unfortunately. So,
Any more questions? You have a question over there?
How much time do you spend analyzing a protocol?
How long did you spend analysing a protocol, or like the Citrix one?
Like the Citrix, but maybe you have also experience with others.
Well, it depends on what kind of length and complexity and depth you need to go into and how much you care about the knowledge. So, or in this particular case of this particular bug, probably a couple of weeks maybe? Can't remember. So long ago. Any more questions?
it's worth stressing the GUI as well also tries to aid you in doing that. So it gives you the ability to inspect, oh, that looks like a length field, right. And then there's like a test harness. You can just run packets through and use your parsers and actually test your theories as to whether those packets actually match up with what you're trying to do.
So if you're running from capture, you're part.
Yeah, you can rerun it against pre-captured packets because the packets are isolated. Once they've been captured in the tool, you can copy them around, paste them around, and just replay them through offline parsing mechanisms to actually then test your functionality.
Any more for any more? Oh, yeah, one at the back.
Yeah, can you differentiate streams in there? I mean, when you have some protocol that it's not all about, single packets, how do you do that?
The question is, can you separate out streams? What about when you've got multiple streams?
Sort of like where the stream has fragments spread across different packets and reassembling them. There is mechanisms to do that. It just becomes slightly more complex to do. It is theoretically possible. It's just, at the moment, there's no simple click and just create a node, unfortunately. But it's something which is on my to-do list to actually add that functionality built in.
Oh, any more?
Cool.
Well, thank you very much for coming.